Good morning, students.
Good afternoon, sir.
Yeah, good afternoon.
Good afternoon, sir.
Yes, good afternoon to all. So that is, shall we start the topic? Okay.
Yes, sir.
So till where we have done, I think,
Aerial expansion, sir.
yeah, aerial expansion is over. Like next to keep subheading the cubicle expansion. Okay. Let us see cubicle expansion. Cubicle expansion. This one. So earlier we have seen that how the linear object is expanded and how the three-dimensional object like plate can be expanded. And similarly, for example, we have considered cuboid. Okay, a cuboid shape object we have considered. So this is a cuboid shape whose length is L, whose breadth is B, okay, whose height is h. So this is length of this cuboid object is L. This is at theta 1 degree temperature. Length is L, breadth is B, and this is let us say the volume is let us say V1 is the volume at this instant. So if the temperature is increases, what we have noticed is that the distance between the two atoms in all possible directions is increases. So the distance between the two atoms in this direction is increases means length of the side, this side is also increases. The distance between the two atoms in this side is increases means the value of B is also going to be changes. The distance between the two atoms in this particular direction is also changes means H is also going to be changes. When L, B, H all are changes means automatically volume of the object is also going to be changes. So we have noticed that for example if the temperature is raised from theta 1 to theta 2. Okay. So this is the shape of an object at theta 2 degree temperature. The length of this side became L prime or L1 or L2 you can keep. So this is nothing but B prime. This is nothing but H prime. So here L prime is more than L because the distance between the two atoms in this direction is increases. If it is heated, similarly B prime is more than B and H prime is H than S. So therefore each side is changing means definitely the volume of the cuboid is also changes. B2 is the change volume at theta degrees centigrade. Then what is the change in volume? So therefore the change in volume, okay, change in volume delta V is equals to V2 minus V1. On what factors the change in volume depends upon means change in volume delta V is directly proportional to the initial volume V1 and the change in volume delta V is directly proportional to the rising temperature delta V. So we can combine this delta V is directly proportional to V1 into delta theta. Proportional is replaced by constant, so then I can write delta V is equal to some proportionality constant gamma V1 into delta theta. So therefore gamma is equals to we can write delta V by V1 into delta theta. So here the proportionality constant gamma is called coefficient of cubicle expansion. How can we define gamma means? The fractional change in volume per degree rise of temperature is known as coefficient of cubicle expansion. This gamma can be written as V2 minus V1 by V1 of delta theta means here temperature is theta 1, here temperature is theta 2 means temperature difference is theta 2 minus theta 1. So that implies here I can write. So gamma value is this is either this expression or this expression, both are representing gamma only. From this equation, what can I write from this equation? V2 that is equals to V1 of 1 plus gamma into delta theta we can write it. So therefore delta theta and this further we can write it V2 that's equals to V1 of 1 plus gamma into theta 2 minus theta 1. So this is about V2 stands for volume of an object at temperature theta 2 whose material is having coefficient of linear expansion gamma and temperature difference is delta 2. This is the final volume. This is the volume V1 where we have considered the temperature is theta 1. So this is about the coefficient of cubicle expansion. Same how we have done a linear aerial. Similarly, here we have done volume. Linear is unidirectional. Aerial expansion is two-dimensional. Cubicle expansion is three-dimensional. That's only the difference. Everything is same. So just what we have considered on heating, the distance between the two atoms in a solid in all possible directions changes. So in this possible direction, in this possible direction, in this possible direction, in all possible directions, the distance between the two atoms in a solid is changes means the rise in temperature causes change in volume also. So then how the volume is going to be changes means according to this relation. The change in volume of an object is directly proportional to the volume of the object which we have considered and temperature difference. So combining this proportionality constant gamma is called proportionality constant, gamma is known as coefficient of cubicle expansion or cubicle expansion coefficient. Gamma can be written as gamma equals to, we can write, the fractional change in volume per degree raise of temperature of an object is known as coefficient of cubicle expansion. That can be written like this. And from this relation, we can write the volume of an object whose temperature, whose coefficient of cubicle expansion is gamma means that V2 can be written as V1 of 1 plus gamma into delta theta. So therefore, V2 equal to V1 of 1 plus gamma into theta 2 minus theta. So like this, we can go with cubicle expansion. How we have gone with the linear aerial, similarly, this is the cubicle expansion. Till here we can write. Till here we can write. We will go through the definition, then you can copy the definition. Till you can write. So got it, students?
Yes, sir.
Yeah. So till here, till the first box you can write it.
Sir, in the second step, delta V is directly proportional to what?
Which one?
The second step, sir, delta V is directly proportional to?
Volume, initial volume.
Okay, sir.
So that V1 stands for initial volume. You can, if you want, we can keep in bracket. Initial volume, delta V is directly proportional to delta theta. The delta theta equals to theta 2 minus theta 1. Completed till here?
1 minute, sir.
Make it. We need to finish this.
Completed, sir.
Yeah. So till here, okay, then you can write. Here the proportionality constant gamma is coefficient of cubicle expansion. Proportionality constant gamma is coefficient of cubicle expansion. It is defined as coefficient of cubicle expansion. It is defined as the fractional change in volume. It is defined as the fractional change in volume per degree rise of temperature. The fractional change in volume per degree rise of temperature of a substance. Temperature of a substance. And you can write these three, this one and this one.
It's not visible, sir.
Yeah, so this is completed. Make a one note before going to write this. Make a one note of this. What is the note means? So just to have a look on it. This is alpha, beta, gamma. These are the coefficients we got. This is linear coefficient of expansion, surface areal coefficient of expansion, and the cubical
Cubicle.
coefficient of cubical expansion. What are the similarities means? What are the common things those are means? This alpha, beta, gamma will have the same units. They will have the same units, and commonly they will depends on the nature of the material. They will not depends on the dimensions of an object such as volume, area, length, etc. So then, what are the factors that is affecting means the dimensions of objects such as length, area, volume. They do not influence this coefficient of expansion. They will depends upon only the material at which the object is made of. Object is made of, and they will have the same SI unit. The SI unit of alpha, beta, gamma are same, and they are depends upon only the nature of the material. Does not depend on the dimensions of the material. For example, if you observe this one, for example, this is a small object which is made up of glass. Okay, which is made up of glass, and this is also an object which is made up of glass. This is also made up of glass. This one. Both are made up of glass. But this is very small, whose size is comparable with this. But what are the similarities means? This object and this object both are made up of the material glass means the cubical expansion coefficient of this object is same as the coefficient of cubical expansion of this, because as these two are made up of the same material called gamma, the value of this gamma does not depend upon the dimensions of an object such as this length, this breadth, and this area, or this volume. So this gamma is entirely dependent upon the nature of the material. So here the two objects is made up of the same material. That's why whatever the value of the cubical expansion for this material is the same. This first cube is same as the second cube. Even though their dimensions are different, also both of them should have the same value of cubical expansion coefficients because they are made up of the same material. That too, the value of the cubical expansion coefficient, either linear or surface or cubical expansion, this alpha, beta, gamma does not depend upon the dimensions of an object, that it depends purely on the nature of the material which it is made of. So, on basis of that, it will depend upon those values. The alpha, beta, gamma value does not depend upon the object. Similarly, for example, here I have taken two rods. This is of 1 meter and this is of some 10 meter rods. Both are, and this is a thick also. When compared to this is a thick rod, this is a thin rod. So this is of 10 meter. Both are made up of iron. So whatever the linear coefficient of expansion
It is
of
the same, sir.
is same as this, because this alpha, these two are made up of the same material that is called iron. This alpha values does not depend upon the dimensions of this length and this area, does not depend upon the dimensions. Because these two are made up of the same material called iron, that's why the expansion coefficients, those are alpha, beta, gamma, they are depends upon the nature of the material, they do not depends on the dimensions of an object. So this is about one more point we need to remember this. Make a note of this. Got it?
Yes, sir.
Yeah, make a note of this. Make a note of this. Okay. Coefficient of expansions. The coefficient of expansions alpha, comma, beta, and gamma. Alpha, comma, beta, and gamma are depends on or depends on or depends on or depends on the nature of the material. Depends on the nature of the material. Depends on the nature of the material. Does not depends on the dimensions of an object. Dimensions of an object. If you want, you can keep such as length, breadth, area, volume, etc. If you want, otherwise no need. That does not depend upon the dimensions of an object, such as length, volume, area, etc. If it is required, you can keep that statement such as, otherwise not required. Okay. So this is the thing. So next one is so observe clearly variation of the density. Okay, variation of the density. So density is equal. What is the formula first of all? Density
Mass per volume.
rho equals to mass by volume. Okay, mass m divided by volume v. So here mass is universal constant. Mass does not change with the temperature, and even it does not change with any other what it is circumstances. Under suitable conditions, this mass can be converted into energy, and energy can be converted into mass. For example, a piece of wood is there. Okay, a piece of wood is there. A piece of wood is burned means then what will be happen when the wood is burned? What will be left finally? Ash is left.
Ash.
Okay. So what was happening there means when the mass is wood is burning on such case, the mass is converted into heat energy and light energy. Mass is converted into energy and energy can be converted into mass under suitable conditions. Similarly, when the petrol is burned, while we are riding a bike or car that is used to run by either petrol or diesel, there is also we are that diesel and petrol are converting into energy by conservation of mass. Okay, so that is anyway coming to this. Mass is universal constant; it does not change with any other conditions. Under suitable condition, this mass can be converted into energy. Energy can be converted into mass. So let it be right. But how about this volume? Means this volume may increase with temperature and may decrease with temperature. So in the density rho is the ratio of m by v. Means even though the numerator is constant, also denominator changes with temperature. Means automatically density is also changes with temperature. If the volume is increases, means density gets decreases. If the volume is decreases, means density gets decreases. It means that most of the substances they can increase their volume with temperature. So therefore, with the temperature, the density of the object is decreases. Most of the substance will contract on cooling. So therefore, the density of the object is increases on cooling. So therefore, mass is constant. Also, volume is changed with the temperature. Because of that, density is also changed with temperature. So therefore, density we can write it as mass by volume. So therefore, I can write density rho is equal to m by v. For example, if V1 is volume at theta 1 degree, so then density rho 1 equal to what can I write at that case? Density equal to mass by volume. Then density equal to mass, m is constant. Volume is, let us say, V1. So that implies V1 equal to, I can write m divided by 1. Similarly, V2 is the volume of an object. Volume at theta 2 degree, then their density rho 2 that's equals to m divided by v2. That implies v2 that's equals to m divided by. So here m is nothing but m is mass, which is constant. Okay, which is nothing but constant. Mass does not vary with time or does not vary with place, does not vary with the temperature, does not vary with the medium. Okay, whatever it is. For example, So if this is an object, okay. So this is an object. If the object is having some 100 grams, means if it is dipped inside the water is also 100 gram, or if it is thrown on the surface of the moon is also 100 gram. It does not depends upon the circumstances, okay, and medium also. That's why m is constant, and rho 1 value, rho 2 value, there we got it. But whatever the volume area we have derived that, so we know that, okay, we know that V2 that is equals to V1 of 1 plus gamma into 1 plus gamma into delta theta. Okay. So then V2 is equal to what can I write? If I substitute this value, m by rho 2 that is equals to m by rho 1 of 1 plus gamma into delta theta. 1 plus gamma into delta theta. This m gets cancelled. That implies 1 by rho 2 that is equals to 1 plus gamma into delta theta divided by rho 1. So if you take the reciprocal of that equation, then we will get rho 2 that is equals to rho 1 divided by 1 plus gamma into delta. So this is about the variation of the density also we can write. Further we can write that rho 2 that is equals to rho 1 of 1 plus gamma delta theta minus. Okay, so then here I am going to use the binomial expansion. What is a binomial expansion? Means 1 plus x, okay, 1 plus x whole power minus n equals to 1 minus nx. N when if x value is much less than 1. Okay, binomial theorem, that is 1 plus nx equal to 1 minus nx if x value is much greater than 1. Similarly, 1 minus x whole power minus n equals to 1 plus nx if x value is much less than 1. X value is much less than 1. So here observe clearly. So here what about this gamma? Gamma is in the order of 10 power minus 4 or 10 power minus 3. 10 power minus 4 means 0.001. This value is much less than this one or comparable with one. This value
Less than 1, sir.
yeah, less than 1. Alpha, beta, gamma is in the order of 10 power minus 3 or 10 power minus 4. That's why alpha, beta, gamma values are very, very small. That's why gamma, delta, theta, this product gamma, delta, theta is also much less than 1. So that's why we can write according to this binomial expansion. Then I can write rho 2 that's equals to rho 1 of 1 minus gamma into delta. So this is a variation of the density of the substance with the temperature. Here delta theta stands for temperature difference. Gamma is the cubicle expansion, and rho 2 is the density at theta 2 degree temperature, and rho 1 is the density at theta 1 degree. So this is the variation of density of an object with the temperature. Got it?
Yes, sir.
So students, this is binomial expansion. Soon you will get in mathematics binomial theorem. Okay, so till then you can remember that if x value is much less than 1, if it is in the form of 1 plus x power minus 1 minus n, then we can write 1 minus nx. Here also gamma, delta, theta is gamma value, alpha value, beta values are much less than 1. They are in the order of 10 power minus 3 or 10 power minus 4. 10 power minus 3 means 0.01, 10 power minus 4 means 0.0001. Those values is much less than 1. So then when x is less than 1, how I wrote in this form? So similarly, it is also in the form of 1 plus x whole power minus 1. That's why I can write 1 minus nx. In place of n, what is there? Minus 1 is there. So this gamma value, alpha value, beta values and are very, very, very small. That's why I can use this binomial expansion and I can write the density. So here mass is universal constant, it does not change. That's why when the volume of an object is changed with temperature means corresponding the density is the ratio of mass by volume. The density is also changed with temperature. How the density is changed with temperature means this is this relation and this relation all represent the variation of the density of an object with the temperature. So this is about the variation of the density with the temperature. Anything else you can ask students?
Sir, in that binomial theorem formula, sir, that is a first one, that is x less than 1, sir.
X is much less than 1.
Okay, sir. In second one?
Second also X is very, very less than 1.
Okay, sir.
Here plus into minus, minus I got. Here minus into minus plus I got. Nothing different.
Okay, sir. Thank you.
Okay. Anything else? So
No, sir.
yeah, copy this. Copy this, then we can go for one of the important thing, that is relation between alpha, beta, gamma. Okay. So write it, make it fast. Done?
Yes, sir.
So right, all of you completed, Anna?
Yes, sir.
Other students, please respond.
Yes, sir.
Yeah. So next one is keep separating relation between alpha, beta, and gamma. Relation between alpha, beta, and gamma. The relation between alpha, beta, and gamma. One of the very, very important. Okay. Relation between alpha, beta, and gamma. Relation between alpha, beta, and gamma. Have a look on it. Okay. First, let me do it. Then we can copy this. Okay. I have taken a cuboid shape, a cube. So this is a cube means all sides are same. That's why this is the side length L. This is also the side length L. This is also the side length L. Okay. Whose coefficient of linear expansion is alpha. Alpha is the coefficient of linear expansion of the material of the cube. So then, what is the area of each face? Area of each face A1. So if you take the area of this face means area equal to side into side. No? L into L means I can write elsewhere. Any side you can take. Either this side L into L, either this side. Okay. Again this L into this is L means this is also L. L into L elsewhere. Area of each face is L square, then volume of the cube that's equals to what we can write as volume of cube. Volume of the cube V1 is equals to volume means length into breadth into height. L into L into L means we can write L cube. So this is an initial condition. Now the temperature of the cube is raised by 1 degree. The temperature of the cube is raised by 1 degree means then what is the each side length it will become? So generally L2 is equals to what we can write L1 of 1 plus alpha into delta theta. L1 L2 that is equals to L1 of 1 plus alpha into delta theta. So therefore what is this side means let me draw the diagram first. Okay. So then what is this side length means the final length I can write L prime that's equals to L of 1 plus alpha into delta theta means what we narrate what is the rising temperature the rising
Theta 2 minus theta 1.
Agree 1 I can write. So then here I can write L prime equal to directly we can write L of 1 plus alpha. So hence this side length is L of 1 plus alpha. What about this side length? This side
L of
length
1 plus alpha.
L of 1 plus alpha. This side length is also we can write L of 1 plus. So this is about each side it will become L of 1 plus alpha. So then what is an each area of each face? So then in this case area of each face, area of each face, I can write A2. A2 is equal to what can I write here? How I wrote side into side L into L square. Here also I can write the side into side means nothing but what is the side into side that is L of 1 plus alpha into L of 1 plus alpha means L square of 1 plus alpha whole square. So then volume of each face. Volume of each face V2. Volume that's equal to what can I write? Volume that's equals to side into side into side means then L of 1 plus alpha into L of 1 plus alpha into L of 1 plus alpha means L cube of 1 plus alpha whole cube. L cube of 1 plus alpha whole cube we get it. Got it all of you?
Yes, sir.
Okay, so what we have taken means just we have considered a cuboid of side length L whose material linear coefficient of expansion of the material is alpha. Okay, whose coefficient of linear expansion of the material is alpha. Then what is the area of each face initially A is L square, volume of the cube that's equal to L cube. Now the temperature of the entire cube is raised by 1 degree. Then what is the length of each side means according to this relation final length that's equal to L1 of 1 plus alpha into delta theta. Here L1 is equals to L and delta theta equals to 1 degree. Then I can write the length of each side. This side is L of 1 plus alpha. This side is L of 1 plus alpha. This side is L of 1 plus alpha. Then area of each face that's equals to A2 equals to L square of 1 plus alpha square. And volume of each face. Volume of cube not face. Volume of cube V2 that's equals we can write side into side into side. This one and this one and this one means L cube of 1 plus alpha whole cube we can. That is about the cube. Then we can go for beta and gamma values. First copy this till here. Students got it what I have considered relation between alpha and beta. Okay na?
Sir, theta 2 minus theta 1, how it became 1 degree, sir?
Just the temperature, for example, now initially is at 50 degrees. Now I have supplied the further heat. The temperature became 51 degrees. What is the rising temperature?
1 degree Celsius.
Like that it is heated.
Okay, sir.
Okay.
Yes, sir.
Anything else? So the first let me say a few sentences regarding this. Okay, consider a cube of side length L. Consider a cube of side L Consider a cube of side L whose coefficient of linear expansion of the material, whose coefficient of linear expansion of the material, whose coefficient of linear expansion of the material is, whose coefficient of linear expansion of the material is alpha, 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 and a cube is heated, a cube is heated, a cube is heated until its temperature is raised by, until its temperature is raised by 1 degree, until its temperature is raised by 1 degree, 1 degree. So you can copy this the diagram and then this. Okay. However, this is L of 1 plus alpha means by using this relation. Length of each side has become L of 1 plus alpha by using that relation. So we make it first. Copy done?
No, sir, 1 minute.
Yeah. Clear? So next, see this we got. So then we know that okay, beta equal what is the formula? Beta equals I can write a2 minus a1 of a1 into I can write delta theta only. The coefficient of okay, so surface expansion coefficient beta a2 value equals to what I got L square of 1 plus alpha whole square, substituting that beta equals to L square of 1 plus alpha whole square minus L square divided by L square of 1. So then beta is equal to what can I write L square of, it is the form of a plus b whole square. Then I can write a square plus b square plus 2ab of minus L square divided by I can write L square. Look at here, alpha is small means what about this alpha square? For example, alpha equals to 1 into 10 power minus 3 is there. Then what about alpha square? If you take alpha square means if you take the square of this value, 1 into 10 power minus 6 it will become students.
Yes, sir.
So it means that alpha is small means alpha square is very small. That's why adding this small value or subtracting this small value, this entire equation does not causes any change. To avoid the complexity of calculation, this insignificant quantities can be neglected. Alpha is small, but alpha square is very small. We can neglect that. If the alpha square is neglected, means then beta is equals to I can write L square of 1 plus 2 alpha minus L square divided by L square. So if L square is taken out and common, it will be cancelled in numerator and denominator. Then beta that's equals to 1 plus 2 alpha minus 1. That implies beta equals to 2 alpha. We can get this is the relation between beta and alpha. This can also be written as beta equals to alpha plus alpha. So this is our equation number 1. So students, very important thing is why we are neglecting the term alpha. So here alpha is very small. Alpha values are significant. I mean very less. For example, alpha that's equal to some 2 into 10 power minus 3 is there. Then how about alpha square? Alpha square, if you take the square of this 4 into 10 power minus 6, it means that 0.0000006 value. So that 0.00006 value is very much less than 1 or not? Very much less than 1.
Yes, sir.
Yeah, if we add those insignificant quantities or if we subtracted those insignificant quantities from the equation, it doesn't cause us any effective change. That's why the alpha square value, very less quantities can be neglected. If it is neglected, then the result remaining equation will become like this. And L square is common in numerator and it can cancel in the denominator. Then we will get 1 plus 2 alpha minus 1. This plus 1 minus 1 gets cancelled. Then beta value will be equivalent to 2 alpha. The same can be written as beta equals to alpha plus alpha. Why we are writing alpha plus alpha? Soon you will know about. So that is about the relation between beta and alpha. So till here you can write down this one till here. Write these 3 steps. I'll narrate one sentence. Write these 3 steps. Make it fast. Students got it why I have neglected this alpha square?
Yes, sir.
Yes, sir.
Yeah. So write it till here you can write. Better? Okay now?
Yes, sir.
Yeah, note down this. Here the term alpha square is very much less and it is insignificant. The term alpha square is very much less. The term alpha square is very much less and it is insignificant. And it is insignificant. And it is insignificant. So it can be neglected. So it can be neglected. So it can be neglected. So therefore beta equals to 100. Till here last one. So the same thing, the same, understand how I have done this?
Yes, sir.
Yeah, same thing. Again, we know that gamma value equal to V2 minus V1 by V1 of delta theta. Substituting that, it is in the form of A plus B whole cube. So therefore, here expand this in the form of. So observe clearly, alpha is less means alpha square is very less. Alpha cube is very insignificant. So that's why the insignificant values such as alpha square and alpha cube is neglected. Then the expression became like this. So therefore, L cube is taken out and minus 1 plus 1 gets cancelled. So then you get gamma equal to 3 alpha. The same you can write. So here if you want, you can write alpha square from alpha cube are okay very small. Okay, alpha square and alpha cube are very small. It can be neglected if you want. You can write. It can be neglected. Alpha square and alpha cube are very small. It can be neglected. Okay, so it can be neglected. It can be neglected like this. Alpha square and alpha cube are very small. It can be neglected. So then I can write gamma equals to 3r. Okay, clear, students? Till here?
Yes, sir.
Anything else you can ask? All the people who are there in the online, please respond. So till here, is it clear or not?
Clear, sir.
Clear, sir.
Clear.
Yes. Any doubts are there in this?
No, sir.
Yeah. So here from equation 1 is what we can write from 1 and 2, you will get beta is equals to 2 alpha and gamma equal to 3 alpha. So then how the relation between beta and gamma means gamma that's equals to gamma equal to right 3 by 2. So this is the relation between gamma and beta. So this is the relation between beta and alpha. This is the relation between alpha and so then I can write alpha is to beta is to gamma is to
Tanakuto.
2 is to. Okay. So that is about from equation 1 it is clear that beta equal to 2 alpha, and from equation 2 we can write gamma equal to 3 alpha. So then how can this gamma and beta can be related? Means gamma equal to 3 by 2 beta. Just you can take the ratio alpha gets cancelled, keep gamma one side and remaining terms on one side. Then you get gamma equals to 3 by 2 beta. So therefore alpha is to beta is to gamma equal to 1 is to 2 is to. So this is about the relation between alpha, beta, gamma means this is only the relation. So that is about the relation between alpha, beta, gamma. Clear, students?
Clear, sir.
Yeah, one note you can write down. This is an application point of view. One note you can write. One note. If alpha x comma alpha x in the sense this one. Okay. Alpha x comma alpha y and alpha z. Alpha x comma alpha y and alpha z are the coefficients of linear expansions. Are the coefficients of linear expansion. The coefficient of linear expansion in three orthogonal directions. In three orthogonal directions. In three orthogonal directions. Then okay. So let me repeat this. If alpha x comma alpha y and alpha z are the coefficients of linear expansion, in three orthogonal directions. Okay, then let me draw the diagram. Okay, so see here. So this is x-axis, this is y-axis, this is the z-axis. Clear, right, guys?
Yes.
Along this direction, the coefficient of linear expansion is alpha. Along this direction, the coefficient of linear expansion is beta. Along this direction, the coefficient of linear expansion is alpha z. So then what is the coefficient of cubicle expansion of this material? How can I write it? Coefficient of cubicle expansion of the material means Earlier you wrote that beta is equal to alpha plus alpha only, no? And gamma equal you wrote this alpha plus alpha plus alpha. There the substance is isotropic substance. It can expand uniformly in all possible directions. Means the coefficient of cubicle expansion is alpha plus alpha plus alpha. But this substance is an isotropic substance whose expansion is different in different direction. Along the x-axis, it can expand at the rate of alpha x. Along y-axis, it can expand at the rate of alpha y. Along z-axis, it can expand at the rate of alpha z. Means the cubicle expansion coefficient of this anisotropic substance gamma equals to alpha x plus alpha y plus alpha z. So if it is isotropic means I can write alpha in all possible directions are same, means these are added together, then we got gamma equal to 3 alpha. So then what is areal coefficient of expansion means so look at here what is an areal coefficient of expansion of this? This is what plane this is? What type of plane this is? YZ plane only. This is students.
Sir.
Yes.
Yeah, this is YZ plane means this side will be expanded at the rate of alpha y. This side will be expanded at the rate of alpha z. Means the area of this face can be expanded by beta, that's equals to alpha y plus alpha z for this plane, this surface. For example, if I consider this surface, then what is this surface? For this surface, this side is expanded at the rate of alpha x. This side is expanded at the rate of alpha z. Means the area is changed by at the rate of alpha x plus alpha z. Like that, different faces of the cube will have a different coefficient of surface expansion. So here this plane is a coefficient of surface expansion of this plane, that's equals to alpha x plus alpha z. For this plane it is alpha y plus alpha z. Coefficient of cubicle expansion of the material, that's equals to alpha x plus alpha y plus alpha z. Only the difference is earlier I have considered isotropic substances. It can expand uniformly in all possible directions. That's why there I got alpha plus alpha plus alpha. But here this is anisotropic substance. It can expand in different directions. So along x-axis side it can expand at the rate of alpha x. Along y-axis side it can expand at the rate of alpha y. Along z-axis side it can expand at the rate of alpha z. Then what is the coefficient of cubic volume expansion rate? Means that's equal to alpha x plus alpha y plus alpha z is the coefficient of cubical expansion. What about the surface? Means each surface will have a different values of surface expansion. This surface will have an expansion coefficient of this. For example, if I consider this surface means if I consider this surface, so this surface is what? So this is a YZ plane, no? So that's why this side of the face is expanded by alpha z. This side of the face is expanded by alpha y. Means the surface expansion coefficient of this surface is nothing but alpha y plus alpha z. So different faces will have different values of beta. Then what is the volume coefficient of expansion of the material? Means alpha x plus alpha y plus alpha. Got it, students? This is anisotropic expansion that goes till now what we have discussed, that is isotropic expansions. Got it?
Yes, sir.
So in JEE, some questions will be there on this particular topic. What they will give means I'll dictate the question also. You can try it. First copy this. This is not required. So understood now this one, why I wrote alpha x plus alpha y plus alpha z. Got it? There 3 alpha I wrote alpha plus alpha plus alpha. That means what? That substance will expand uniformly in all possible directions. That's why I wrote alpha plus alpha 3 alpha. But this is a different substances. They can expand in different manner in different directions. That's why I wrote gamma value is alpha x plus alpha y plus alpha z. Got it?
Yes, sir.
Any doubts are there in this?
No, sir.
Yeah. So first draw the diagram, then I will narrate one sentence, then you can write this. First draw the diagram.
Sir, you did not complete the note point, sir.
Which one, Mama? That only, no?
Sir, of linear expansion, that's all, yes, sir.
Please read that once.
Sir, if alpha x, comma alpha y, and alpha z are the coefficients of linear expansions in three orthogonal directions, then
In three orthogonal directions, then draw this diagram and I will narrate this point. Wait.
okay, sir.
Okay, so make it fast, almost 1 o'clock. Okay, na?
Completed, sir.
So right, note down this. The coefficient of cubical expansion of the material is the coefficient of cubical expansion of the material is the coefficient of cubical expansion of the material is gamma equals to alpha x plus alpha y plus alpha z. Alpha x what gamma equal to alpha x plus alpha y plus alpha z. Okay.
Okay.
So note down this question. You can leave. Note down this question. You try it this. Okay. The coefficient of linear expansion of the coefficient of linear expansion of the material. The coefficient of linear expansion of the material in one direction is alpha 1. In one direction is alpha 1. In one direction is alpha 1. And every perpendicular direction is alpha 2. And every perpendicular direction is alpha 2. And every perpendicular direction is alpha 2. What is the cubical expansion coefficient of the material? What is the cubical expansion coefficient of the material? I am repeating the question. Okay, a substance whose alpha 1 is the linear coefficient, expansion of the linear coefficient of the material, and in every perpendicular direction the coefficient of linear expansion is alpha 2, then what is the coefficient of cubical expansion? Okay, so this is one of the advanced questions which was given in a few years back. Okay, so not now, it is more than 6-7 years back they have given this question in advanced single correct answer type. So try it answer. So let us discuss if not getting the answer in tomorrow's class. Okay. So is it clear, guys? Anything else you can ask?
No, sir.
Okay. All of it clear? Any doubts are there?
No doubt, sir.
No
No
doubt,
doubt,
sir.
sir.
So guys, okay, right, guys. See you on tomorrow's class. Okay.
Thank you,
Thank you,
sir.
sir.
Bye,
Sir.
sir.
Thank you,
Okay.
sir. Bye, sir.
Thank you to all. Bye.